this approach can be applied in statics, which means mechanics material, and in dynamics, pretty much you will see in your vibrations in the fall. Okay, this method is pretty powerful, very powerful, and sometimes it can provide insights into these systems, certain systems. And the first one, in terms of the mechanics material, and the first one I would talk about what is the strain energy density and how to calculate the density. And so here we're using the examples of the longitudinal, okay, so for this case, and again, we have a sample. A sample is under loading. The loading is applied slowly. Basically, we say quasi-static. Okay, so that means we don't want to imply too quick and to induce any dynamic influence. And pretty much from your vibrations next semester, you will see if, say, I have this loading like this, okay, and this is kind of the point loading, impulse loading. The impulse loading usually kind of including the momentum of the dynamic. The equivalent, it will produce the equivalent amount of the loading is 2 times of the load I apply. And that is the influence of dynamic loading. So that means for our mechanics material, if we will apply this loading too quick, then basically you will induce additional amount of the load. Okay, that is what we don't want. So we like to keep the quasi-static. That means everything deformed will be under static equilibrium slowly. Although we know that won't be possibly achieved, but that is the ideal we try to achieve. So usually, for the testing, we don't have the experiment, but during the testing, the loading rate is very small, very slow. Okay, so under these situations, we can say if this is a cross section of A, so we record the loading P and divide by the area, and this will have the stress, and then we record the deformation delta divided by original length L. This is our strain. So in computers, we have strain, we have stress. If this material, in general, doesn't matter is ductile or brittle, in certain range, initially the relation is a strain line. Okay, so here we only talk about the elastic domain, and this is a strain line. Okay, until a certain point, reaching the yielding point or yielding strains, then that's a different story, and we can drop that one here. Okay, and again, if your application of the loading is not slow, then you won't get this linear curve, I guarantee. Okay, so under this situation, we can get a strain curve, the strain line, and that the slope is E, and basically this is called the Young's modulus. Okay, so now with this curve, we can talk about the strain energy density. So the strain energy density, we usually using U, lowercase u, and so basically U is simply equal to, for example, if you want to calculate the strain energy density to a certain point, in general, we just give a delta epsilon. Corresponding to the epsilon here, we have the corresponding stress. So basic stress equal to epsilon times E. So the strain energy density That means we apply the loading, this elastic object is deformed just like rubber ring or spring. We deform it, and spring, you know there's a density stored there, and we call the strain energy density. And basically the density is simply graphically is defined by this area. Okay, so that is the equivalent that is equal to the slashed area shown. And in mathematics, basically that's equal to 1/2. This is a triangle, and the triangle has the side epsilon, has a height sigma. That's it. And then we using this notation, basically this one. Further, you can have the few expressions. So this is epsilon times sigma. So this can be equal to 2 times E epsilon square, or if you like, you can become like this. Okay, so basically here, using notation is sigma equal to E times epsilon, and here you use notation epsilon equal to sigma divided by E, either way. Okay, graphically representing by this triangle. Okay.